like I said, we're gonna spend the first part of today, maybe the first half of what's left, going through and looking at some more examples of redox reactions and how to assign numbers and that kind of thing. So if you're not finished with this, that's okay. Everybody started at kind of slightly different times because of when you finish the proficiency. But let's try to walk through this example problem here. So what we're dealing with is we've got sulfuric acid, H2SO4. And so there are two approaches that we can take to this because it's an acid. We can deal with it like a molecular compound and just make one long algebra problem. 2 hydrogens and sulfur and 4 oxygens equal the total charge on the sulfuric acid, which is nothing. And then from there, it would be a matter of looking at each individual atom and going, okay, well, I know that the oxygen is going to be -2 because oxygen's almost always -2 when it's in a compound. And I know the hydrogen is going to be +1 because hydrogen is always +1 when it's in a compound with other nonmetals. And so if I apply those, then I get a total of +2 for the hydrogens in total, plus sulfur, plus a total of -8 for the oxygens. Do a little bit of algebraic solving here. 2 plus -8 is -6. So the sulfur must be +6. So that would be one approach that we could come up with. The hydrogen is +1, the sulfur is +6, and the oxygen is -2. Now, to address one of the questions that came up this morning, well, why aren't we putting hydrogen as +2 and oxygen as -8? Why isn't -8 one of the options here? What we have to remember about oxidation numbers is that they are assigned on a per atom basis. So even though the total charge for the oxygen is -8, each oxygen individually is only -2. And that's what we're concerned with oxidation numbers. We're looking at the individual charge on one atom in that compound. So each of the hydrogens is +1, each of the oxygens is -2, and the sulfur is +6 because it's the only one there. Now, another way that you could have taken this is if you recognized, well, you know what? Acids are basically ionic compounds. Because we know that when we put an acid into water and dissolve it, it breaks apart into the hydrogen ion and whatever ions are left. So if I did that, I could recognize, okay, I've got the hydrogen ion and the sulfate ion. Well, the hydrogen ion, that one's easy to assign. It's +1 because it's the only atom there and it has a charge. For the sulfate, I would need to go through a similar kind of process. Sulfur and 4 oxygens make the total charge of -2. And since each oxygen is -2, this would give us -8 again for all of the oxygens collectively, which would lead me to the same +6 conclusion that I got to for the sulfur using the other method. So both methods here are perfectly fine and easily acceptable. It just comes down to kind of what makes the most sense for you. And the only time where we would really do something like this is when we have an acid, when we have an acid, because acids kind of exist in both worlds. They're covalent compounds. They're made up entirely of nonmetals. And we also know that they have ionic characteristics as well. They will split apart. Any questions with this example before we move on to a little bit more complicated of an example that we're going to work through together? All right, so here's that more complicated example that we're going to be working through. This is an example of a literal rocket science kind of question. When rockets are fired in space, it is the result of the reaction of hydrazine and dinitrogen tetroxide in space. And the reason why it's these two, these are very easily liquefied substances, so you can carry a larger payload of liquid much more safely than you could a larger payload of gas, which would have to be held at a pretty consistent pressure in order to keep it in the gas phase. So you'd be able to take up a whole lot less in doing so that way. Here's what our task is. We know the products of this reaction are nitrogen gas and water vapor. What are the elements oxidized and reduced? What is the oxidizing agent and reducing agent? And so for this question, what we want to look at is we have to assign oxidation numbers. So as far as assigning oxidation numbers go, let's look at the hydrazine first. For the hydrazine, N2H4, what that means, I've got 2 nitrogens and 4 hydrogens, and together they are going to give me no charge because hydrazine is a neutral molecule. From here, I would look at, okay, the hydrogen is going to be +1 because hydrogen with nonmetals is a +1 state. So I've got 4 +1s, so that's +4. So rewriting this equation, 2 nitrogen plus 4 is equal to 0. Well, if I follow the algebra the rest of the way through, 2 nitrogen would be equal to -4 since I had to subtract the 4 from both sides, and nitrogen would be a -2 overall once I divided by that 2. So I'm just going to make a habit of writing the oxidation numbers over top of the chemical formula, just so that I know which number goes with which element. So the nitrogen was -2, the hydrogen was +1. Now down here, we'll do the N2O4, the dinitrogen tetroxide. And so that one breaks into 2 nitrogens and 4 oxygens, giving us a total charge of 0 because that molecule is also uncharged, neutral. Here we can fall back on the fact that we know that the oxygen is going to be -2 because oxygen is almost always -2 when it's in a compound. And so I've got 2 nitrogen plus -8 is equal to 0. Adding 8 to each side, 2 nitrogens is equal to +8, which means that the nitrogens are +4. So I've got a +4 charge on each of the nitrogens in the second reactant and a -2 charge on the oxygens. What is the oxidation state for the nitrogen in the product? Isaac's got it. Does anybody else? It's an element, right? Okay. Even if I'm getting tripped up by the fact that there's a 2 there, walk through the problem with yourself. I've got 2 nitrogens and it's a total charge of 0. Well, if I divide each side by 2, 0 divided by 2 is still 0. So any elemental substance where everything in that particular molecule is the same element is going to have a 0 charge on it unless that molecule also has a charge. So, if I'm looking at mercury 1 ion, for example, Hg2, 2+, obviously the oxidation state on that substance isn't 0 because the thing is charged. But what is the actual oxidation number? Well, it's +1. I got a 2+ ion divided by 2 atoms. So each ion, each atom, has a +1 charge. That's how we get to mercury 1 out of that particular cluster. That's why mercury 1's kind of weird in that sense. The reason it's +1, the reason it's the mercury 1 ion is because that 1 is actually referring to its oxidation state, not its charge. For water, well, this one's actually pretty easy because we've got hydrogen in a compound and oxygen in a compound, and so they just kind of fall to their default states. +1 for hydrogen, -2 for oxygen. And if we did the math, it would work out. So now we've assigned all of the oxidation numbers. Now we have to take that and move it into figuring out what is being oxidized, what is being reduced. And so what we want to look for are changes. So I can see that the hydrogen has not changed in this reaction. It was +1 before, it's +1 after. I can see that the oxygen hasn't changed. It was -2 before, it's -2 after. What has changed is the nitrogen. And it's actually a weird circumstance here because what we're seeing is that nitrogen is changing both for the oxidation and for the reduction, but in 2 different compounds. So in pink here, we can see that the nitrogen in hydrazine is going from a -2 state to a 0 state. It is getting more positive, less negative. So that means that it has lost electrons. The loss of electrons is oxidation. So if I'm identifying the oxidation process here, I would identify the nitrogen in the hydrazine as being that element that was oxidized. Now for the reduction, let's put this one in orange. I can see that in the case of the nitrogen in the dinitrogen tetroxide, we're going from the +4 state to the 0 state. We are getting more negative, less positive. That means that we're adding electrons. The gain of electrons is reduction. Thank you. And so when we describe the reduction process here, we're talking about nitrogen, in this case, in the form of the dinitrogen tetroxide. And so we've got an odd circumstance here where we've got the same element being oxidized and reduced, but where it makes sense is the fact that they're coming from different compounds. Now we get to maybe the more trying task. How do we identify the oxidizing agent and the reducing agent? Because it can be really easy to get these confused. What we have to remember is that the oxidizing agent is the substance that forces oxidation. And so what substance is forcing oxidation? It's the dinitrogen tetroxide. Because it is forcing the oxidation of this nitrogen in hydrazine. What is the reducing agent? Well, it's the other reactant. It's the hydrazine. And remember, this is a process that happens simultaneously. The oxidizing agent and the reducing agent are forcing the action on the other at the same time. So you can think of it as the oxidation agent comes over to the reducing agent, and immediately the reducing agent hands over the electrons that the oxidizing agent needs. In that process, we get oxidation occurring in one of the elements in the reducing agent. We get reduction occurring in one of the elements in the oxidizing agent. Both things happen at the same time. And yes, it's a little bit confusing, but we can kind of think of these are paired processes. The oxidizing agent gets reduced, the reducing agent gets oxidized because it forced the other thing to do what it was supposed to do. Questions on this before I let you try something similar? Okay, so I'm going to give you a pair of questions here in Top Hat. Now, the good news is they are considerably simpler. They are considerably simpler than the one that we just did. So let's start with the first part here. Assign oxidation numbers to everything and figure out which element is being oxidized and which element is being reduced. These compounds are not nearly as complex as the ones that we just did. So we're dealing with either ionic compounds or elements. So what should the state for the elements like zinc and copper be? Yeah, they should be zeros. For the others here, again, they're ionic compounds, so we should be able to split them into their ions. We know oxygen is the oxide ions -2. And so from that perspective then, for charge balance purposes, the zinc is going to have to be +2, and the copper is going to have to be +2. So I've got oxidation state of +2 and -2 and 0 on the reactant side, +2, -2, and 0 on the product side. So now we have to go through what's changing So are we seeing any changes with oxygen here? -2 before, -2 after. Okay, so we know oxygen's going to be the odd man out here. It's going to be the response that doesn't get paired because it doesn't get oxidized or reduced. Now it comes down to, we've got copper going from +2 to 0. So what's happening there? Are we getting an increase in positivity or a decrease? Getting a decrease. It's going less positive. So if it's going less positive, that means that it's getting more negative. If it's getting more negative, that means it has to be adding electrons. So the gain of electrons is, everybody together now, reduction. So that would mean that the copper is being reduced. Now you could do this by process of elimination. You could also kind of follow along here. The zinc is going from 0 to +2. So it's getting more positive, which means less negative. Less negative meaning fewer electrons. It's losing electrons. The loss of electrons is, everybody together now, oxidation. So that would mean that the zinc is being oxidized here. So our answer here, we just got to flip-flop those first two answers. All right, on to the second part. We identified the oxidation and reduction processes in the first part. What is the reducing agent here? And so ignore this typo here. The second option should be copper 2 oxide solid. So first and foremost, right away, you should automatically eliminate answers C and D. Oxidizing agents and reducing agents are always reactants. Zinc oxide and copper are products in this particular reaction, so they can't be oxidizing or reducing agents. Now it comes down to which one is the reducing agent, which one is going to be oxidized in the process. Well, we already established that. Zinc was oxidized, which means zinc is going to be the reducing agent in this case. And so in this case, since zinc is the reactant as well as the element, it serves both purposes. If zinc were part of a larger compound, then the reducing agent would be that compound that contained zinc. But in this case, the compound that contains zinc and zinc are the same thing. It's just solid elemental zinc. All right, any questions with redox? Hopefully this helps a little bit if you're kind of not sure after what last night looked like. And so if you weren't sure about last night, if you didn't finish that assignment, remember, it's still there. 95% credit is still a lot better than 0% credit. So if you didn't finish it completely, the parts that you didn't finish are still there for 95% credit today. Take advantage of that. With our last 10 minutes, we're going to talk a little bit about putting some numbers to stuff. And in particular, we're going to talk about concentration. So concentration has been sort of the thing that's been running through the background of lab. We've talked about it a little bit. We've talked about things like, oh, this is a concentrated solution, or this is a dilute solution. We've used terms like 0.1 m, 0.5 m, 2 m, but we really haven't talked about what those things mean yet. Now we get the opportunity to do so. The reason we need to talk about concentration is because when we look at things in solution, the thing that is actually interesting to us is also the thing that is the least present in that solution. Every solution has a whole bunch of water that's getting in the way of us being able to measure it accurately. So if I want 50 grams of sodium chloride and I've got sodium chloride solution, I can't just measure out 50 grams of that sodium chloride solution. I'm not going to get what I want. I'm going to get a whole lot of water and maybe a couple of grams at most of sodium chloride. And that's not going to be what I need. So concentration allows for us to kind of work in that system. And it follows into two different pathways. Both of them are ratios, fractions. The pathway on the left here is really useful when we are dealing with phase changes or with things happening where temperature independence is not necessarily possible. For this course, we're not going to need that kind of fine tuning. That's something you'll see in Chem 106, those of you that have to take it. For the most part, we're going to focus on this kind of calculation over here on the right, what concerns ourselves with how much solute is there compared to how much solution is there. And there are really two directions that we can go off of this kind of calculation. One is based upon masses, and one is based upon moles. The one that is based upon masses, we've seen before, mass percent. Now, in the context we used mass percent in Module 2, we were mainly looking at the mass percent of a given element in a larger compound. We use that as the basis for determining empirical formulas. We saw it a little bit in the Module 4 quiz this week. How much calcium is there in 35 grams of calcium phosphate? Mass percent was a big part of those kinds of calculations. The only difference here is that we're looking at a solution instead of a compound. And so for the solution, we become interested in what is the solute, how much of it do I have, and what is the overall mass of the solution that I'm taking that solute from, or that I'm mixing that solute into. That becomes the basis of my mass percent. Now, this has some application, and there is some place where we use this, and it's useful to us. But primarily, we're going to focus more on the moles, because the moles, as you know, are a gateway to stoichiometry. And if we haven't learned anything in the past couple of weeks, stoichiometry is kind of a big deal in chemistry. Molarity is that way that we can get them to interact with each other. With molarity, we calculate the moles of solute over the liters of solution. So when I describe to you an acid as being 12 molar hydrochloric acid, what I'm saying is that in 1 liter of that acid, you will find 12 moles of hydrogen chloride. And so you could do further calculations off of that relationship. There is a practice problem in here. The practice problem we aren't going to do. We're just starting to run out of time here. I want to make sure that we're up with the other class. If you want to see it fully worked out, the annotated notes in Blackboard have this problem fully worked out for you. The overall process is relatively straightforward. It's nothing you haven't seen before. Since we are trying to turn everything into moles of barium chloride over liters of solution, what we need to do is we need to convert this grams into moles, and we need to convert these milliliters into liters. I'd encourage you to try that on your own, see if you can come up with the answer, and then check it against the annotated PowerPoint in Blackboard and see if you got it right. Our last point here for today, though, I just wanted to talk about this a little bit because you saw this to some degree when you were doing the spectrophotometry lab. It's the idea of a dilution. So one way to make a solution is the way that we just talked about, what you saw on the practice slide. I take out a mass of a certain substance, I dissolve it in a certain amount of water, I figure out its calculation and its molarity that way. But what if I wanted to make a solution and instead of using the solid material, I wanted to use a stock solution like this? This is a standard solution, 1,000 part per million lead. Well, what if I wanted to make a solution that was only 50 parts per million lead? How would I go about doing that? Well, this is where the dilution equation comes in. Now, the dilution equation has many different forms. You've seen one that is similar to this one in your lab manual. M1V1 is equal to M2V2. There's also a more generic one out there. C1V1 is equal to C2V2. The overall premise here is pretty straightforward. When I take a sample of this solution, the number of moles in this sample is not going to change, regardless of how much water I add to it. So if I take, this is 50 milliliters, if I take half of it, 25 milliliters, the amount of parts per million of lead are going to be the same. Regardless if I take that 25 milliliters and dilute it up to 1,000 milliliters, or if I take that 25 milliliters and dilute it up to 50 milliliters. The amount of lead will be exactly the same in both cases. What will change is the total volume. And so the beauty of this equation is because that is the same, because the amount of moles of the solute does not change, once I pull that out, I can be very liberal with what my concentration units are. So this focuses on molarity, but it doesn't have to be molarity. It can be parts per million. It can be grams per liter, like it was in the spectrophotometry lab. It can be molarity. It can be mass percent. It doesn't matter. So long as the unit of measurement is the same on both sides of the equation, the dilution equation will work. And that's not just for the concentration. That works for the volume as well. I don't need to have my volume be in liters to get this to work. It can be in milliliters. It can be in centiliters. It can be in liters. It doesn't matter. So long as the unit is the same on both sides, the equation will work because the units will end up canceling. So we're going to leave it right here for today. Where we're going from here. On Wednesday, we'll talk a little bit about some other kinds of calculations that we can do with molarity. We'll talk first about titrations, because that's what you've seen most recently. And we'll also extend it to non-titration stoichiometry, where we look at things that are not necessarily related to molarity, but can also solve other kinds of problems, like how many grams do I need? How many moles am I going to get? Kind of a more generic framework. If you haven't done this yet, go ahead and do so. Otherwise, I'll see you on Wednesday. Enjoy those extra couple of days.